Welcome to this unit number 3 and lecture number 3, that is classification of problems based on initial condition and or boundary condition. So, what are the learning objectives? Learning objectives first is to identify the initial and boundary conditions for hydraulic systems. Second, to distinguish between the problems based on initial and boundary conditions. So, what is this initial condition? Initial condition describes the initial state of the system in terms of dependent variables. Example, initial water level and velocity in a channel network, that should be defined for starting the simulation, and initial groundwater level in an aquifer system or aquifer region if you want to start groundwater simulation, and that should be time dependent. The types of boundary condition, depending on the location, we can define boundary conditions as external boundary condition defined for external or outermost locations. Example is upstream and downstream locations of a river. We can define either inflow condition, discharge, or in the downstream section we can define depth for a particular river system. River boundary for a aquifer region, we can define constant head boundary for aquifer region, or we can vary that depending on the physical system. Internal boundary condition defined for internal locations. Operating conditions for hydraulic structures within channel network. Sometimes these internal boundary conditions for channel networks are also called as junction conditions. Constant water level maintained in a pond, often aquifer region, that is also our internal boundary condition. If the pond is situated within the in the central portion of the aquifer region, then we can consider it as internal boundary condition. Then depending on the physical nature, we can again classify this boundary condition. First one is called as Dirichlet or specified boundary. Example, discharge specified at inlet or outlet in channel network. Neumann boundary, that is flux boundary. In flux boundary, example is no flow boundary near impermeable region in a aquifer system. Let us say that we have a rock boundary, then obviously there will be no flow situation in the aquifer system, and we can consider that as zero flux boundary. Robin or mixed boundary, it is the combination of Dirichlet and Neumann condition, essentially weighted combination of Dirichlet and Neumann. So, depending on the type of differential equation, either it is ordinary or partial differential equation, we can classify that based on this initial and boundary condition. So, in differential equation, if you have ordinary differential equation, then first type is initial value problem. In this one, we need a governing equation or G and initial condition. Next type is our boundary value problem. In this one, we need governing equation plus boundary condition. Now, if we talk about partial differential equation, then the types are boundary value problem. There we need governing equation and boundary condition, and initial boundary value problem or IBVP, where we need governing equation, initial condition and boundary condition. So, let us talk about this initial value problem. One simple example is gradually varied flow in open channel. The governing equation is represented like this: y is the depth of flow, x is the longitudinal direction, and S naught is the bed slope, SF is the friction slope, 1 minus Fr square. Fr square is the Froude number, Fr is the Froude number, and in this case we can specify the initial condition. That means at a particular location in the channel, maybe we can consider that as x is equal to 0 location, we can define our water depth. So, y naught is the water depth specified at that location. So, this kind of problems where we have governing equation and initial condition, we can call it as initial value problem for ordinary differential equations. Now, the example of boundary value problem for ordinary differential equation can be given by this steady one dimensional groundwater flow in unconfined aquifer. Let us say that we have, this is x direction and this H2 and H1, these two are actually specified water levels on both sides. That means these two are Dirichlet kind of boundary condition or specified boundary conditions, and perpendicular to this, that is y direction, we will consider that there is no variation in that direction. So, this is basically for H x problem. H is varying with x only. If we have constant levels of H2 and H1 with time. So, this problem can be represented as boundary value problem, where governing equation is, this is actually equation of or combined equation of mass and momentum, essentially d qx by dx is equal to F is the mass conservation equation, and for qx we can define this minus t dH by dx as the equation, and which is actually momentum equation, and we can combine this to get this differential equation. Interestingly, in this case H is varying with x only. Now, if we consider the boundary condition, that means on the left side, if we have this H2 as specified head boundary and L is equal to Lx, that is on the right hand side H is H1, which is again specified boundary. So, we have two specified values for this problem. So, this problem is actually boundary value problem for ordinary differential equation. Now, let us talk about groundwater movement in aquifers. In this case, we are not considering the situation where there is no variation in the y direction. Let us say it is constrained by no flow condition within this Ly distance, then your problem gets slightly modified, because we need to consider the Qy component here along with Qx, and if your H2 and H1 these values are not varying, then we can get a steady state situation, because there will not be variation of water level within the system. So, essentially that is your boundary value problem. We have no flow on these two sides and specified head in these two directions. That means we have two Neumann boundaries and two Dirichlet boundaries. So, if we talk about contaminant transport, in that case again your left and right boundaries are constant head, which is linearly varying from 90 to 89 and 87 to 85, and these two boundaries are impermeable or Neumann boundaries, and we have sourcing term available at this location. So, water or contaminated water is injected within the system. So, in this problem time varying injection is there. So, obviously time varying condition will be there. So, with time there will be variation in head values. So, we can consider this problem as boundary value problem, the initial boundary value problem for partial differential equations. Again, let us say that we are considering channel networks. Basically, these are our inlet sections and these two are our outlet or O. This is I1, I2 and I3, these three are inlet, O1, O2 are outlet. So, I1, I2, I3, O1, O2, these are your endpoints or outermost points. In this case, boundary conditions are specified. However, for internal points 1, 2, 3, 4 and 5, we generally define the junction conditions, or these are actually your internal boundary conditions. So, junctions conditions, your inflow and outflow in a particular junction, that should be same, and energy conservation, if we do not consider this velocity head, then we can simplify with this form. If we consider this surface flooding, so what are the boundary conditions? So, we need to define the outer boundary. So, obviously, there should be no flow condition, or there should be no flow from this boundaries, and this is your internal channel condition. So, obviously, from channel there is lateral inflow to the surface area, and water spreading is there because of this channel inflow or inflow from the channels. And obviously, in this case, this is your junction condition position, this is your inlet condition, this is our outlet conditions. So, 1, 2, 3, these 3 locations we need to specify the boundary conditions or external boundary conditions, and for this internal node we need to specify the internal boundary conditions 1, 2, 3, these 3 locations. So, we can get this kind of surface flooding situation. So, again that is your time varying problem, and open channel flow, in this case U, W, these two are our variables. We have this initial condition, that means U equals to U2 and W equals to 0, that means no velocity in the vertical direction, and only the longitudinal velocity value is U2 initially, and with time we can change the inlet velocity and we can get the desired hydraulic jump simulation. Again, for pressurized conduits, for left and right hand case, this fixed head is maintained. So, obviously, closure time of valve should be known to specify the conditions, and again this is one dimensional system, but this is again initial value initial boundary value problem. For pressurized conduits, again we have mass conservation and momentum conservation equation, we have internal conditions or junction conditions, we have boundary conditions. So, we can solve this problem as initial boundary value problem. Surface water groundwater interaction. So, obviously, the bottom boundary is impermeable. This boundaries, these two boundaries on the left and right hand side can be either specified or no flow boundaries, and top surface, as this is our depth averaged equations we generally use for this case. So, we will have unique depth value or unique water level value will be there. Surface water groundwater interaction. Again, for this case we need to define the interaction mechanism between the channel flow and our groundwater system. We have this Hg, Hr values for either river or groundwater system. The interesting point is that in this groundwater equation solution, we can either specify Hg or groundwater head value as specified head boundary or specified head boundary, and there can be situations where we can define it as flux boundary. N is the vector which is normal to the boundary or unit vector, and this Qn is some specified value of flux. There can be situation where we have mixed boundary. Why this is called as mixed boundary or Robin kind of boundary condition? Because Qc is again dependent on this Hg value. So, using this Hg and Hr, we can change the flux condition. So, although this kind of boundary condition is bit complicated, but it combines both specified head and flux boundary condition. And if you are talking about 1D, 2D integrated system like our 1D channel flow situations, we can define either internal or external boundary conditions, internal boundary conditions in terms of junction conditions, and surface flooding situations, and we can define the boundary condition for this area, either flux boundary or no flow boundary, and this condition is actually your channel flow condition. We can specify the hydraulic structure corresponding internal conditions for this system. So, depending on the physical situation within hydraulic system, we can change the boundary conditions, and in the combined form along with governing equations, we can try to solve our problem using this governing equations and boundary conditions. So, either they can be ordinary differential equations or partial differential equations. Next lecture we will try to discuss the problem classification based on the nature of solution.